So let's discuss how to find the areas in the polar coordinates, or areas inside or under the polar curves. Okay? So for example, if your curve is given as cosine of r is equal to the cosine of 2 theta, do you remember what kind of curve is this? It's going to be a rose, a flower with four leaves, right? So for example, I would like to find the area of one of the leaves. So what I need to do. Again, so we are going to use the integration in order to find the areas. So do you remember how we got this integration, the definite integration? So our idea to find the areas was to split the area into the small rectangles, right? And to just sum the areas of those rectangles, right? So here, I would like to split the areas to the small sections. Or do you remember? So if we have the section of a circle with the radius r and with the angle theta, the area of the section is going to be equal to 1/2 r squared theta, where the theta is measured in radians. For example, if the theta is equal to the 2 pi, it should give you the area of the whole circle, right? If you substitute the theta with the 2 pi, it's going to be pi r squared, right? 1/2 r squared multiplied with the 2 pi, it's pi r squared, right? So actually, this formula comes from like a linearly dividing this like a 2 pi to the thetas, okay? If you measure the theta in the in radians, you can find the area of this sector of the circle with the radius r by multiplying the theta to the square of the radius and divide this to the 2. Okay? So now let's say we're given a curve in the polar coordinates. Like this kind of curve. And I would like to find the area of the curve between the two angles, two thetas, theta 1 and theta 2. Okay? I would like to find this area, basically. This curve is given as the function. R is equal to the f of theta, right? So this curve is given, R is equal to the f of theta. What does it mean, f of theta? It means that if I'm going to choose the different angles here, it's going to tell me how much the points are far away from the origin. Basically, it's going to tell me the distances, right? From the origin until the points, right? For example, if I would like to know what is the distance between the origin until this point, for example, this distance, I need to evaluate the function at the phi 1. You understand this? If this angle is pi 1, for example, this might be pi over 5, right? Pi over 5, this theta 1, sorry. Then if I would like to know what is the distance between this point and the origin, I just need to evaluate this function at this theta, right? Okay. The idea of defining the area would be to split this area into the many sections. So let's split this. So basically, I'm splitting this into the many sections. Okay? And do you remember before, if I split this to the many sections, when we used to have the curves in the rectangular coordinate system, the distances or the width of the subintervals was delta x, right? Do you remember what we did? So we subtracted the a from the b and divided to the n, the number of the subintervals. It gives us the delta x, right? So delta x was b minus a divided to the n, right? So here, I'm going to through theta 1 and theta 2, and I need to split a lot of angles, like angles between the theta 1 and theta 2 to the many small angles, right? So basically, I'm going to define d theta. It's going to be theta 2 minus theta 1 divided to the n, okay? So you're finding the area between the two angles. In order to find this, we've decided to split this into the many small angles, okay? All of these angles are going to be delta theta, Okay, delta theta, not d, delta, sorry. This angle is going to be delta theta. Okay? Now, could you please tell me, can I approximately take it as the kind of a section, all of them? For example, I would like to find the area by summing the areas of the sections. Okay? What is the area of one section here, of this one, approximately? 1/2 r squared multiplied to the theta, right? So what does it mean, the r? Is the distance between the point and the origin, right? How I can find the distance between the point and the origin? By evaluating the function at this angle, at the theta, right? For example, in this case, we're going to evaluate the function at the theta 1, and then I'm going to square this, and then I need to multiply this to the angle. So what is the angle of the sector of the first one? Delta theta, right? Delta theta. So let's evaluate the second area. So second area is equal to 1/2 r squared theta. It's going to be 1/2. What is the radius for the second one? It's going to be, it's like a theta t, right? Theta t is equal to the theta 1 plus delta theta, right? So this is going to be f of theta 2 in the square multiplied to the delta theta, right? So I decided to split this area into the many sections, okay? And by finding the areas of all the sections and by summing all the areas, I can roughly find this area, right? The area between the angles theta 1 and theta 2 is going to be roughly as the summation of 1/2 f of theta I in the square multiplied to the delta theta. I goes from 1 to the end. Okay? So I'm going to find this approximately. I'm saying this approximately because I'm leaving out this areas. Do you see those areas? I'm making some error here, right? So I'm not taking account this small areas here. And in order to get more precise result, I need to increase the number of the sections, right? So the exactly area would be the limit of the summation of the areas of the sections, where n goes to infinity. If I just increase the number of the sections, it's going to give me the exactly the area, right? But this is nothing else so I can define this limit using the integration. Using the definition of the definite integral, we can write this as the integration of the 1/2 f of theta in the square d theta from theta 1 to the theta 2. Okay? So this is how we're going to find the areas in the polar coordinates. Okay? So now let's go back to our example with the four leaves of the flower. I would like to find this area. Okay? This curve is given as the cosine of 2 theta. In order to find this area, I need to define the angles. Right? In order to find this area, I need to define the angles. From which angle to which angle I need to integrate. Right? From which angle to which angle I need to integrate. So could you please tell me roughly what are those two angles? So what is this angle? And what is this angle? So this is minus pi/4. And this is pi/4. Right? Do you see? So this line splits the quarter exactly at the half. Right? So if 1/4 is pi/2 and half is going to be pi/4. Right? So actually, if you change the theta here, from minus pi/4 to the pi/4, you're going to get one leaf. Okay? So you're going to go through all the points on this leaf. If you're going to change the theta from minus pi/2 until pi/2, you're going to go through all the points on the first leaf, on this leaf of this curve. Okay? So I would like to find its area. In order to find this area, I need to apply this formula. right? So the area here is going to be integration of from minus pi over 4 until pi over 4, 1 over t multiplied to, what was the f of theta? Cosine of 2 theta in the square, right? Multiplied to the d theta. Okay? So r is equal, so f of theta is equal to the r actually, right? R is equal to the f of theta. Okay? Let's integrate this and evaluate this. So it's going to be integration from minus pi over 4 until pi over 4. So I'm going to write this cosine square of theta can be written as 1 plus cosine of 4 theta. Right? Divided to the 2. Yes? So do you remember what was the cosine of 4 theta? Cosine of 4 theta is cosine square of 2 theta minus sine square of 2 theta. And 1 can be written as cosine square of 2 theta plus sine square of 2 theta. Right? So this is 1, this 1. And this is the cosine of 4 theta. If you divide this to the 2, it's going to be, you can cancel this sign and this sign. You're going to have cosine square of 2 theta. Right? So basically, we can write down this cosine square of 2 theta as 1 plus cosine of 4 theta over 2. Right? 1 plus cosine of 4 theta over 2. Sorry. So in order to integrate this, let me open up the brackets. It's going to be 1 over 4 plus 1 over t cosine of 4 theta, and its integration from minus pi over 4 until pi over 4. The theta. So what is the integration of the 1 over 4? What is the antiderivative of the 1 over 4? It's 1 over 4 theta. And what is the antiderivative of the cosine of 4 theta? It's going to be 1 over t multiplied. Antiderivative of the cosine of 4 theta. It's sine of 4 theta. And I need to multiply this additionally to what? To the 1 over 4, right? Because of the substitution rule, right? Or like if you take a derivative of the sine of 4 theta, because of the chain rule, it's going to be cosine of 4 theta multiplied to the 4, right? And this 4 is going to be canceled with this 1 over 4, and you're going to have exactly this chain. Okay? So we need to evaluate this at minus pi over 4 and pi over 4. So let us substitute the pi over 4 everywhere. So it's going to be 1 over 4 multiplied to the pi over 4 plus 1 over 8 of sine of, what is the 4 multiplied to the pi over 4? It's pi, right? Minus 1 over t multiplied to the minus pi over 4 plus 1 over 8 multiplied to the sine of minus pi, right? So we know that the sign is 0 at every pi. So this is going to be 0, and this is also going to be 0. So the final answer is going to be pi over 16, and this is going to be plus pi over 16, and this is going to be pi over 8. Okay? The area of the one leaf of this flower is going to be equal to the pi over 8. So let's discuss how to find the arc lengths. So we are going to adopt a formula for the arc lengths to here. Okay? So arc lengths. In order to find the lengths of the curves, we're going to use the parametric form, parametric equations, and the polar coordinates. Do you remember what was the parametric curves for the polar coordinates? It was x is equal to the r of theta multiplied to the cosine of theta, and y is equal to the r of theta multiplied to the sine of theta. Okay? Do you remember this? Okay. So do you remember also how to find the lengths of the curves using the parametric equations? There was a formula. The lengths of the curve in the parametric form, for the parametric curves, it's going to be the integration from alpha to the beta, right? The square root of the derivative of the x with respect to the parameter, right? dx dt in the square, plus derivative of the y with respect to the parameter, in the square, then taking the square root, and with respect to the theta. Okay? So the formula previously, our parameter was t, and we used to write it as length is going to be equal to the integration of square root of x dot in the square plus y dot in the square. Okay? So before we start, we need to take the derivative. We need to know what is the derivative of the x and derivative of the y. So let's simplify this, okay? So I'm not going to use the formula for the arc lengths in this form. I would like to simplify this a little bit. So do you remember what was the derivative of the x with respect to the theta? It's going to be r prime multiplied to the cosine of theta, right? So let me write r prime. R prime is going to mean the derivative of the r with respect to the theta, okay? R prime cosine of theta minus r sine of theta, right? Because it's going to be the multiplication of the first function r to the derivative of the cosine, which is minus sine. What is the dy dr? D theta, sorry. R prime sine plus r cosine, right? Because derivative of the sine is plus cosine, right? So there it is minus because the derivative of the cosine is minus sine, right? Now I just need to substitute this formula and this formula to here, okay? Let us find what is the x prime in the square and y prime in the square, okay? So dx d theta in the square plus dy d theta in the square is equal. So I'm going to square this term, okay? And I'm going to use the formula. Do you remember a plus b or a minus b in the square? It's going to be a squared minus tab plus b squared, right? Okay, let's apply this. It's going to be r prime square cosine square, right? Minus r prime cosine of theta multiplied to the sine of theta. Then what is the third term? I'm using this. Plus r square sine square, right? Plus, I need to now the square of this term, right? Do you remember which formula I need to use? A plus b in the square is going to be the square of the first term plus tab plus b squared. So what is this, the square of this term? It's going to be r prime in the square sine square plus r theta sine of theta cosine of theta plus what? R square cosine square of theta. Okay? Now, do you see that this term looks like this one? They are actually the same, but one is coming with the plus and one is coming with the minus, so I can just eliminate them, right? Okay? So if I eliminate them, and also, do you see that here in this term, I've got the r prime in a square, and in this term, I've got the r prime in a square. I'm going to take them out from the brackets, okay? So let me write this down. R prime in a square, so this is equal to. If I take out the r prime square from the first term, it's going to be cosine square. If I'm going to take this from this term, it's going to be plus sine square, right? Also, I see that this term and this term are the same, right? I'm going to take the r square from the brackets as well. So it's going to be r square. If you take out the r square from the first term here, what is left? Sine square. If you take out the r square from the second term, what is left? Cosine square. Okay, so what is the formula? R prime square plus r square. Okay, in the first time, like this is not r. This is r prime. Okay, because this is 1 and this is 1. So the formula of the arc lengths becomes the square root of r prime plus r prime square from the square root integration with respect to the theta from alpha to the beta, from where the theta is changing until which value of the theta it is going to change. Okay, this is the formula of the arc lengths for the polar curves. Yeah, I mean, derivation is not so difficult, right? I mean, it's long, but it's not difficult. So in a case, if you forgot this formula, you can just quickly retrieve this. Okay, so let's discuss the arc lengths for the cardioid, but not the usual cardioid was the 1 plus sine of theta. Let's discuss this how to find the for the cardioid was the cosine. Do you remember if I write down the r is equal to the 1 plus cosine of theta, it's going to be this kind of term, this kind of curve. Okay, roughly. They should be symmetric. Okay? Now, in order to find this area, the arc lengths, I'm going to find the arc lengths from here until here. Okay? So from theta is equal to 0 until theta is equal to pi. Okay? Then since that is symmetric, I can just multiply this to the t in order to find the arc lengths of the whole cardia. Okay? So let's going to apply this formula. So do you see in this formula, I need to know what is the r, and also I need to know what is the r prime. Right? So what is the r prime? R prime means derivative of the r with respect to the theta. So this is going to be minus sine of theta. Okay? Then the arc length is going to be the integration of the square root. R squared, which is going to be 1 plus cosine of theta in the square, plus minus sine of theta in the square from the square root. And we need to integrate this with respect to the theta from 0 until pi. Right? Okay, so let's open up the brackets. It's going to be the integration from 0 to the pi, square root of 1 plus t cosine of theta, plus cosine square of theta, plus, what is the square of the minus sign? It's going to be sine square d theta. So this is going to be the integration from 0 to the pi. I can write it. So do you remember that this is going to be 1, right? Sine square plus cosine square is going to be 1. And I can write this as a t plus t cosine of theta, d theta. Okay? So now I need to somehow get rid of the square root, right? So if you take out the t from the square root, it's going to be 1 plus cosine of theta. Do you know how to, what to do in order to get rid of the square root? So actually, you can write this as square root of t integration from 0 to the pi, 1 plus cosine of theta, d theta. Okay? So what I need to do in order to get rid of the square root, 1 plus cosine of theta, I need to figure out how to write this with a square. Okay? Do you remember before, we used to have the square inside the integrand, and we tried to use the formula of the half an angle or double angle in order to get rid of the square, in order to decrease the square, decrease the power, right? Now I need to try to increase the power, right, up to the square. Is it possible to rewrite 1 plus cosine of theta as something different with the square? Okay, is it possible to rewrite 1 plus cosine of 2 theta as something with the square? 1 plus cosine of 2x is something with the square. Okay, so do you remember what was the 1 plus cosine of 2x? It was cosine square plus sine square is the 1, right? Plus cosine of 2x is going to be cosine square minus sine square. It can be written as a t cosine square of x, right? So what about 1 plus cosine of x? Is it possible to write this in the same way? Yes, so if I take the x as a double angle, I can write this as a t cosine square of x over t. Right? Okay, so I'm going to write this as square root of t, the integration from 0 to the pi. The inside the square root, 1 plus cosine of theta, I'm going to write as t cosine square of theta over t. Okay? If you take out this t with the square root of t, it's going to be t integration of cosine of theta over t, because the square is going to be canceled with the square root, right? So from 0 to the pi d theta. What is the antiderivative of the cosine? Is sine plus sine, right? And I additionally need to multiply this to the t because of this 1 over t, right? Because if I would like to take the derivative of the sine of theta over t, it's going to be cosine of theta over t multiplied to the 1 over t, and this 1 over t is going to cancel with this t, and I'm going to have this t, right? Okay, so this is going to be integration from 0 to the pi. So let's put the pi, it's going to be 4 sine of pi over 2, right? Because I need to substitute the theta with the pi, right? Minus 4 sine of 0 over 2, right? The second term is 0 because sine of 0 is 0. And the first term here is, what is the sine of pi over 2? Is 1. So this is going to be 4. Okay? The arc length of the half cardioid is equal to the 4. What is the arc length of the whole cardioid? Is 8, right? The arc length of the whole cardioid is 8. So this is how we need to find the arc lengths for the polar curves.